Hello there, and welcome to Science with Sleepy. I'm so glad you found your way here. Maybe you had a long day, or maybe you're the kind of person who likes falling asleep to deep thoughts about the quiet machines that circle our planet rather than counting sheep. Either way, tonight's journey is for you. You've got nothing to do but rest. Let your mind relax, your breathing slow, and your body grow light as if gravity itself has softened. Because tonight, we aren't simply thinking about technology. We're drifting through the silent world above, where thousands of satellites orbit our planet, invisible to most of us, but essential to almost everything we do. They connect continents, watch weather, help us find our way, and expand our understanding of Earth and space. But beneath their quiet work lies something deeper. Questions about how they stay up there, how they work, and how they've transformed our world. We'll travel gently from the first beeping satellite to the thousands that circle us today, from the physics that keeps them aloft to the ways they've changed how we live. You'll hear of orbits and gravity, of signals traveling at light speed, of satellites that watch storms and satellites that guide us home. Some of what you hear tonight may surprise you, or at the very least spark some curiosity as you drift off to sleep. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. Now let's begin. Right now, as you rest, there are thousands of satellites circling Earth. They're up there, right now, doing their quiet work. Some are as small as a shoebox, others are as large as a school bus. Most of them you can't see with the naked eye, but they're there. Watching, listening, connecting. And they've changed everything about how we live, without most of us ever thinking about them. So let's ask a simple question. What is a satellite? And how did we get here? Chapter 1. What is a satellite? A satellite is simply something that orbits around something else. That's it. It's not complicated. The moon is a satellite. It orbits Earth. Earth is a satellite too. It orbits the sun. But when we talk about satellites, we usually mean the artificial ones. The ones humans built and launched into space. The ones that do our work up there in the dark. The word satellite comes from Latin. It means attendant or follower. That's what satellites do. They follow, they orbit. They circle around. The moon follows Earth. Our artificial satellites follow Earth too. They're our attendants in space, doing jobs we can't do from down here. Before we had artificial satellites, we only had one, the moon. It's been there for billions of years, lighting our nights, pulling our tides, watching over us. But the moon can't make phone calls, it can't predict weather, it can't help you find your way. So we decided to build our own. We decided to put machines in space. The idea of artificial satellites isn't new. People have been thinking about it for a long time. In 1869, a writer named Edward Everett Hale wrote a story about a brick moon, a giant brick sphere that would orbit Earth and help ships navigate. It was fiction, but it showed that people were already imagining satellites long before we could build them. In 1928, a scientist named Herman Potocnik wrote about space stations. He imagined platforms in orbit that could observe Earth. He called them space mirrors. He was thinking about the future. He was imagining what might be possible. But it wasn't until the 1950s that we actually tried. The Soviet Union and the United States were in a competition. They wanted to be first. They wanted to prove they could reach space. They wanted to show the world what they could do. The first one was called Sputnik. It was launched on October 4, 1957. That's not that long ago. Your grandparents might remember it. Maybe your great-grandparents. It was a moment that changed everything. Sputnik was a small metal ball, about the size of a beach ball. It weighed 184 pounds. It had 4 antennas sticking out like whiskers. And it beeped. That's all it did, it beeped. Scientists at the time estimated that Sputnik would be visible to about 6 million people on Earth. They were right. People all over the world looked up. They saw something new, something human-made, something in space. But that beeping was heard around the world. People could tune their radios and hear it beep, beep, beep. A steady signal from space. For the first time in human history, something we built was circling the planet, sending signals back. People went outside at night with binoculars and tried to see it. A tiny point of light moving across the stars, faster than any plane, higher than anything had ever been. The beeping signal was on a frequency that amateur radio operators could pick up. They spread the word. They told their friends. Soon, everyone knew. There was something in space, something we built, something beeping. The beeping lasted for 22 days, then the batteries died. Sputnik kept orbiting for 3 months, then it fell back to Earth and burned up in the atmosphere. But by then, everything had changed. The space age had begun. We had proven that we could put something in orbit. We had proven that we could reach space. Historians note that Sputnik's launch marked the beginning of the space age. Before Sputnik, space was just an idea. After Sputnik, it was a reality. We had done it. We had reached space. We had put something in orbit. The impossible had become possible. Sputnik was built by the Soviet Union. It was part of the space race, a competition between countries to explore space. But Sputnik did more than win a race. It opened a door. It showed that space was reachable, that we could put things up there, that we could use space for our purposes. The launch of Sputnik surprised many people, especially in the United States. They thought they were ahead. They thought they would be first. But the Soviet Union beat them. This created urgency. This created competition. This pushed both countries to go faster, to do more, to reach further. Just a few months later, the United States launched Explorer 1. It was smaller than Sputnik, but it did more. It carried instruments. It discovered something amazing. The Van Allen radiation belts. These are zones of charged particles that surround Earth, held in place by our planet's magnetic field. Explorer 1 found them by accident. Its instruments detected radiation that shouldn't have been there. Scientists realized that Earth is wrapped in invisible belts of energy, protecting us from the worst of space radiation. The discovery was unexpected. The scientists who built Explorer 1's instruments thought they might find some radiation. But they found much more than expected. The readings were off the charts. At first they thought their instruments were broken. But they weren't. They had discovered something new. Something important. Something that changed how we understand our planet. This discovery changed how we understood our planet. Earth isn't just a rock floating in space. It's a complex system with magnetic fields and radiation belts. It's protected, it's special, and we might never have known this without that first satellite. Space scientists now know that the Van Allen belts are crucial. They protect Earth from dangerous radiation from the Sun. Without them, life on Earth would be much harder. The belts are like a shield. An invisible shield, protecting us from space. The Van Allen belts are named after James Van Allen, the scientist who designed the instruments on Explorer 1. He didn't expect to find them. He was looking for something else. But his instruments detected radiation. More radiation than anyone expected. This was a surprise. A good surprise. A discovery that changed science. Since then, we've launched thousands more. Today there are over 5,000 active satellites orbiting Earth. That's a lot. But there are also thousands of dead ones. Satellites that ran out of power. Satellites that broke. Satellites that completed their missions and were turned off. All of them still up there, circling, silent. Space agencies track these objects. They keep catalogs, they know where everything is. They monitor for collisions. They watch the sky. They keep track of all the satellites, active and dead. It's a big job, but it's necessary. The number of satellites is growing fast. Every year, hundreds more are launched. Companies are putting up constellations. Countries are expanding their fleets. Students are launching their own. The sky is getting crowded. But it's also getting more useful. According to space tracking organizations, the number of satellites has doubled in just the past few years. The growth is accelerating. More satellites are being launched now than ever before. The sky above us is changing, rapidly, constantly. The International Space Station is technically a satellite too. It's the biggest one we've ever built. It's about the size of a football field. It weighs almost 1 million pounds. And people live on it. Right now, as you're listening, there are astronauts floating inside it, looking down at Earth, doing experiments, living in space. The space station orbits Earth every 90 minutes. That means the astronauts see 16 sunrises and 16 sunsets every day. Can you imagine? Day and night, over and over, faster than you can blink. Astronauts on the space station experience something unique. They see the whole planet. They see it turn. They see storms. They see cities at night. They see the aurora. They see things we can only imagine. They have a perspective that's impossible from the ground. The space station has been up there since 1998. That's over 25 years. It's been continuously occupied since 2000. That means there have been people living in space, non-stop, for over 20 years. The space station is a home. It's a laboratory. It's a symbol of what we can do when we work together. Scientists have conducted thousands of experiments on the space station. They've studied how plants grow in space, how materials behave, how the human body adapts. They've learned things we couldn't learn on Earth. The space station is a unique laboratory. A laboratory in space. A laboratory that orbits. But most satellites are much smaller. Some are tiny. Cube SATs are satellites the size of a loaf of bread. They're cheap to build. They're cheap to launch. Students build them. Companies build them. Countries build them. You can put a CubeSat in space for less money than a car costs. This has open space to everyone. You don't need to be a superpower to have satellites anymore. The first CubeSat was launched in 2003. Since then, thousands have been launched. They've become a standard, a way to do space science affordably, a way to teach students, a way to test new technologies. CubeSats got their name because they're built-in units. One unit is a cube, 10 centimeters on each side, that's about 4 inches. You can have 1 unit, or 2 units, or 3, or more. They stack together like building blocks. This makes them easy to build, easy to launch, easy to use. The standard size makes everything easier. Standard launchers, standard deployment systems, standard components. This standardization has driven down costs. It's made space accessible. Students all over the world are building CubeSats. High school students, college students. They're learning about space. They're doing real science. They're putting their own satellites in orbit. This is amazing. A few decades ago, only governments could do this. Now students can do it too. Some student CubeSats have made real discoveries. They've studied the atmosphere, they've tested new technologies, they've done real science. These aren't just learning projects, they're real satellites, doing real work. One student CubeSat studied how bacteria survive in space. Another tested new solar panel designs. Another measured radiation levels. These are real experiments, real science, done by students, launched into space. working alongside professional satellites. The impact goes beyond science. Students learn, they gain experience, they become the next generation of space engineers. They become the people who will build the satellites of tomorrow. CubeSats aren't just satellites, they're training, they're education, they're the future. Other satellites are huge. Communication satellites can be as big as a school bus. They need to be big because they carry huge antennas and powerful transmitters. They need to send signals across thousands of miles. They need to cover entire continents. So they're built large, with solar panels that unfold like wings, stretching out to catch sunlight. When these big satellites launch, they're folded up. They fit inside a rocket, but once they're in space, they unfold. Solar panels extend, antennas deploy, they transform, they become much larger than they started. It's like a butterfly emerging from a cocoon, but made of metal and solar cells. The deployment is critical. If something goes wrong, the satellite might not work. Solar panels might not extend, antennas might not deploy, the satellite might be useless. So engineers test everything. They test on Earth. They simulate space conditions. They make sure everything works. They can't afford mistakes. Once deployed, these satellites are huge. Their solar panels can span over 100 feet. Their antennas can be the size of a house. They're massive, but they need to be. They need to send signals across thousands of miles. They need to cover entire continents. Size matters. What do all these satellites have in common? They all orbit, they all circle Earth, they all need power. Most use solar panels. Big flat panels that turn sunlight into electricity. They all need computers to control them. They all need antennas to talk to Earth. They all need to know where they are. They all need to point in the right direction. Solar panels are crucial. Without power, a satellite is dead. It can't do anything. It can't communicate. It can't take pictures. It can't do its job. So satellites are covered in solar panels. They're like solar-powered machines, floating in space, powered by the sun. But solar panels don't work in the dark. When a satellite goes behind Earth, it's in shadow, no sunlight, no power, so satellites have batteries. They store energy when the sun is shining. They use that energy when they're in the dark. It's like charging your phone, but the satellite does it automatically, over and over as it orbits. The batteries are crucial. Without them, satellites would die every time they go into shadow. They need enough battery power to last through the dark periods. They need to store enough energy to keep working. It's a constant cycle. Charge in sunlight, use in shadow, charge again, use again, over and over. Battery technology has improved. Modern satellites have better batteries. They last longer, they're more efficient, they're more reliable. This extends satellite lifetimes. It makes them more useful. It makes them more valuable. Early satellites had short lifetimes. Their batteries died quickly. Their components failed. They lasted months, maybe a year. Modern satellites can last decades. They're built to last. They're built to survive. They're built to work for a long time. Some satellites have exceeded their expected lifetimes. They keep working years after they were supposed to stop. They're like old cars that just keep running. They're reliable. They're tough. They keep doing their jobs long after they should have stopped. When satellites finally do fail, they often have end-of-life plans. They're moved to graveyard orbits. Or they're deorbited to burn up in the atmosphere. They're given proper endings. They're disposed of responsibly. They don't just become space junk. The computers on satellites are special. They have to work in space, in vacuum, in extreme temperatures, in radiation. They have to be reliable. They have to work for years without breaking. They're not like your laptop. They're built tougher. They're built to survive. Space is harsh. Temperatures swing from extreme heat to extreme cold. Radiation can damage electronics. Vacuum can cause problems. Satellites have to handle all of this. Their computers have to keep working. They can't fail. Too much depends on them. Engineers use special components, radiation-hardened processors, special memory, redundant systems. Everything is designed to survive, to keep working, to be reliable. A satellite computer failure can mean mission failure. So everything is built to last. Antennas are how satellites talk. They send signals to Earth. They receive signals from Earth. They're like the satellite's voice and ears. Without antennas, satellites are silent. They can't communicate. They can't do their jobs. Satellite antennas come in many shapes. Some are dishes. Some are arrays. Some are simple rods. They're all designed to send and receive signals. They're all designed to communicate. They're all essential. The antennas have to be precise. They have to point in the right direction. They have to aim at the right spot on Earth. A small error can mean the signal misses. So satellites have systems to keep their antennas pointed correctly. They're constantly adjusting, constantly aiming, constantly communicating. But here's something interesting. Most satellites you can't see. Even on the clearest night with the darkest sky, you probably won't see them. They're too small. They're too far away. They don't shine bright enough. The ones you can see are usually the space station, or satellites with large solar panels that catch sunlight and reflect it down to us. But most satellites are invisible. They're up there, working, but you'll never know they're there unless you're looking for them. The International Space Station is the easiest to see. It's big. It's bright. It moves across the sky like a slow star. You can see it with your naked eye. You can even see it from cities, if you know when to look. There are websites that tell you when it will pass over your location. You can go outside and watch it. A bright point of light, moving steadily, silently, across the stars. Some satellites are designed to be seen. There was a project called Humanity Star. It was a satellite shaped like a disco ball. It had 65 mirrors that reflected sunlight. When it passed overhead, it would flash, creating a bright point of light that moved across the sky. The idea was to create a shared experience. Anyone on Earth could look up and see it. It was visible for a few months before it fell back to Earth. But while it was up there, people all over the world looked up and saw the same light, at the same time, and knew that we're all under the same sky. There have been other visible satellites too, some with reflective surfaces, some with lights, some that flash in patterns. They're rare, but they exist. They remind us that there are machines up there, that we've reached space, that we've put things in orbit. Satellites come in all shapes and sizes. But they all do the same basic thing. They orbit, they circle, they follow Earth around and around. But how? How do they stay up there? Why don't they fall? That's where the real magic begins. That's where physics takes over. That's where we discover that satellites aren't floating. They're falling. They're just falling in a very special way. Chapter 2. The Physics of Staying Up. Here's a secret about satellites. They're not floating. They're falling. All the time. Every second, they're falling toward Earth. But they're moving so fast sideways that they keep missing. They fall, but they fall around. They fall in a circle. They fall in an orbit. This might sound strange. How can something be falling if it never hits the ground? How can it fall forever? The answer is in the speed. Satellites are moving so fast that by the time they fall a little bit, they've moved forward so much that Earth has curved away. They're constantly falling, but they're constantly missing. It's like they're falling around a corner that never ends. Imagine you throw a ball. It goes forward a bit, then falls to the ground. Now imagine you throw it harder. It goes farther before it hits the ground. Now imagine you throw it really, really hard. So hard that by the time it falls the distance to the ground, Earth has curved away underneath it. The ball is still falling, but it's falling around Earth. It's in orbit. This is what Isaac Newton figured out over 300 years ago. He imagined a cannon on top of a very high mountain. If you fire the cannonball slowly, it goes a short distance and falls. Fire it faster, it goes farther. Fire it fast enough, and it goes all the way around Earth and comes back to where it started. That's an orbit. Newton wrote about this in his famous book Principia Mathematica. He described how objects could orbit, how they could fall around instead of falling down. He understood the physics long before we could test it. Newton never saw a satellite, he never saw a rocket, but he understood the physics. He understood that if something moves fast enough, it can fall around Earth, instead of falling to Earth. He understood orbits before we could create them. Physicists today still use Newton's laws to calculate orbits. They're still accurate, still useful, still the foundation of how we understand motion in space. Newton figured it out over 300 years ago, and we're still using his math today. Gravity is always pulling. It's pulling you down right now. It's pulling satellites down too, but satellites are moving so fast that they keep missing Earth. They fall, but they fall in a curve. They fall in a circle. Or an ellipse. They fall around and around, never hitting the ground, never escaping into space. They're in perfect balance. This balance is delicate. If a satellite moves too fast, it will escape. Gravity won't be strong enough to hold it. It will fly away into space, never to return. If it moves too slow, it will fall. Gravity will win. It will spiral down and burn up in the atmosphere. But at just the right speed, it stays, it orbits, it falls forever, without ever landing. The speed needed for orbit is called orbital velocity. It's different at different heights. Close to Earth, you need to go faster. Far from Earth, you can go slower. It's all about balancing gravity and speed. Too fast, and you escape. Too slow and you fall. Just right, and you orbit. The speed depends on how high you are. Satellites in low orbit, close to Earth, need to move very fast, about 17,000 miles per hour. That's fast, really fast. A bullet travels at about 1/700 miles per hour. So satellites are moving 10 times faster than a bullet. At that speed they circle Earth in about 90 minutes. They see the whole planet in an hour and a half. To put that in perspective, if you could drive a car at 17,000 miles per hour, you could drive around the world in about an hour and a half. But you'd need a very special car, and very special roads. And you'd probably need to be in space, because that's where satellites are. But satellites higher up move slower. They don't need to go as fast because gravity is weaker up there. Gravity gets weaker as you move away from Earth. So satellites far away don't need as much speed. A satellite 22,000 miles up moves much slower. It takes 24 hours to orbit once. The same time it takes Earth to rotate once. So if you put a satellite at exactly the right height, moving at exactly the right speed, it will stay over the same spot on Earth. It will seem to hang there, motionless, even though it's moving thousands of miles per hour. These are called geostationary satellites. They're perfect for things like TV broadcasts. The satellite dish on your roof points at one spot in the sky. It doesn't need to move. The satellite is always there. Always in the same place. Always ready to send signals. Geostationary orbit was first proposed by a scientist named Arthur C. Clarke in 1945. He wrote a paper about it. He imagined satellites that would stay in one place, always over the same spot on Earth. He thought they could be used for communication. He was right. Today, most TV satellites are geostationary. They're always there, always ready, always in the same place. Clarke was a science fiction writer. But he was also an engineer. He understood the physics. He understood what was possible. He predicted geostationary satellites decades before they existed. He saw the future. And he was right. Today, geostationary orbit is crowded. There are hundreds of satellites there. They're spaced carefully. They can't be too close together. They need room, but there's limited space. It's a valuable resource, a limited resource, and it's getting more crowded. But most satellites aren't geostationary. Most are in low Earth orbit. They zip around quickly. They see different parts of Earth with each pass. They're perfect for taking pictures, for watching weather, for mapping. They see the whole planet every day, just by going around and around. Low Earth orbit is popular because it's close. Signals travel faster, pictures are sharper. But satellites there move fast. They're only over one spot for a few minutes. Then they're gone. But that's okay. They come back, they orbit, they see everything eventually. The International Space Station is in low Earth orbit. It's about 250 miles up. At that height, it needs to move at 17,000 miles per hour to stay in orbit. The astronauts inside feel weightless. But they're not really weightless. Gravity is still pulling them, they're just falling. They're falling around Earth. And because they're falling at the same rate as the space station, they float. They feel like there's no gravity, but gravity is there. They're just falling together. This is what orbit feels like. You're falling, but you're falling around. You're falling in a circle. You're falling forever. It's beautiful, really. The perfect balance between falling and flying, between gravity and speed, between coming down and staying up. Astronauts describe it as floating, but they're not floating, they're falling. They're just falling in a way that feels like floating. It's a strange feeling. Everything floats, water floats, food floats, you float. But it's not magic, it's physics, it's falling. Different orbits are good for different jobs. Low orbits are close, you can see details, you can take sharp pictures, but you move fast. You're only over one spot for a few minutes, then you're gone, circling around to come back later. High orbits are far, you can see more of Earth at once. You can stay over one spot. But you're far away. Details get fuzzy, you can't see small things. You trade detail for coverage. You trade closeness for stability. Some satellites have special orbits. Polar orbits go over the North and South poles. They see the whole planet as Earth rotates underneath them. They're perfect for mapping, for watching ice caps, for seeing everything. Polar orbits are interesting because Earth rotates underneath them. A satellite in polar orbit goes from north to south, or south to north. But Earth is spinning east to west. So the satellite sees different parts of Earth with each pass. Over time, it sees everything, the whole planet, every square mile. This makes polar orbits perfect for mapping. A satellite in polar orbit can map the entire planet. It just takes time. It sees a strip on each pass. Earth rotates. The next pass sees a different strip. Over days, weeks, months, it sees everything. It builds a complete picture. Weather satellites often use polar orbits. They can see the whole planet. They can track weather systems. They can see how storms move. They can provide global coverage. It's perfect for their job. Other satellites have elliptical orbits. They're close to Earth sometimes, far away other times. They're like stretched circles. These are good for studying different parts of space. Close in, they study Earth's atmosphere. Far out, they study the space around Earth. Elliptical orbits are like ovals. The satellite moves faster when it's close to Earth, slower when it's far away. This is because of gravity. Close to Earth, gravity is stronger, so the satellite moves faster. Far from Earth, gravity is weaker, so it moves slower. It's like a swing. You move fastest at the bottom, slowest at the top. This speed variation is useful. When the satellite is close, it can study Earth in detail. When it's far, it can study space. It gets the best of both worlds, close-up views and distant views, all in one orbit. Some scientific satellites use elliptical orbits for this reason. They study Earth when close. They study space when far. They maximize their scientific value. They get more data. They learn more. Some satellites have very elliptical orbits. They come close to Earth, then swing far out. These are called Molniya orbits. They're used by Russian satellites. They spend most of their time far from Earth, but they come close periodically. This is useful for communication in high latitudes, where geostationary satellites don't work well. But no matter what orbit they're in, they're all doing the same thing. They're falling around Earth, they're balancing speed and gravity. They're staying up by constantly falling. It's physics, it's simple, but it's also magical. These machines we built are falling forever, and that's how they work. Orbits aren't perfect circles, they're usually ellipses. Some are very elliptical, some are almost circular, but they all follow the same rules. They all balance gravity and speed. They all fall around Earth, never hitting it, never escaping. The shape of an orbit depends on the satellite's speed and direction when it was launched. If it's launched at exactly the right speed, in exactly the right direction, it will have a circular orbit. If it's launched faster or slower, or in a different direction, it will have an elliptical orbit. Both work, both are stable, both keep the satellite in space. Launch is critical. The rocket has to put the satellite in exactly the right place, at exactly the right speed, in exactly the right direction. Small errors can mean big problems. The satellite might not reach orbit, it might end up in the wrong orbit, it might not work at all. That's why launches are so carefully planned. Every detail matters, every calculation matters, every second matters. Get it right, and the satellite works for years. Get it wrong, and millions of dollars are wasted. It's high stakes, it's precision, it's rocket science. Engineers spend years planning launches. They calculate trajectories. They simulate orbits. They test everything. They leave nothing to chance. They check and double-check. They verify and verify again. Because once a satellite is launched, you can't fix mistakes easily. The launch window matters too. The best time to launch depends on where you want the satellite to go. Sometimes you need to launch at a specific time. Sometimes you have a window of just minutes. Miss the window, and you wait. Wait for the next opportunity, wait for the right moment. Once launched, the satellite has to deploy correctly. Solar panels must extend. Antennas must deploy. Everything must work. If something fails during deployment, the satellite might be useless. It's a critical moment. A moment that determines success or failure. Now that we know how they stay up, let's see what they're actually doing up there. Because staying in orbit is just the beginning. The real magic is in what satellites do. How they connect us. How they watch over us. How they help us understand our world. Chapter 3. Connecting the world. Imagine you want to call someone on the other side of the world. Maybe they're in Tokyo and you're in New York. How does your voice get there? It could go through cables under the ocean, miles and miles of fiber optic cables, snaking along the seafloor. But it could also go through space. Up to a satellite, bouncing off it, and back down to the other side of the planet. In less than a second. This is what communication satellites do. They're like mirrors in the sky. They catch signals from one place and bounce them to another. Radio waves travel up. The satellite receives them. Then it sends them back down, aimed at where they need to go. The whole trip takes a fraction of a second. The signal travels at the speed of light. 186,000 miles per second. Fast enough to circle Earth 7 times in 1 second. Before satellites, long-distance communication was hard. You needed cables, you needed wires, you needed physical connections. But cables can break, they can be expensive, they can't reach everywhere. Satellites changed that. They made communication wireless. They made it global. They made it possible to talk to anyone, anywhere, anytime. The first communication satellite was called Telstar. It launched in 1962, just 5 years after Sputnik. We were still learning, still experimenting. Telstar was different. It could receive signals from Earth and send them back. It could relay television. It could relay phone calls. It could connect continents. Telstar was a collaboration. It was built by AT&T, but it was a symbol of what was possible. It showed that satellites could do more than just beep. They could carry information. They could connect people. They could change how we communicate. The first live TV broadcast across the Atlantic happened because of Telstar. People in Europe could watch something happening in America, live as it happened. This was magic. Before satellites, TV signals could only travel in straight lines. They couldn't curve around Earth. They couldn't cross oceans. But with a satellite up there high enough to see both continents, the signal could go up and come back down. It could bridge the gap. That first broadcast showed a baseball game, a simple game, but it was being watched live, across an ocean, in real time. People in Europe saw it as it happened. This was unprecedented. This was the future. This was what satellites could do. The broadcast was a test. But it worked. It proved that satellites could carry television. It proved that we could share live events across oceans. It proved that the world could be connected. In real time. Instantly. After Telstar, more communication satellites followed, each one more capable, each one connecting more people, each one making the world smaller. Each one bringing us closer together. Today, communication satellites do so much more. They carry TV signals, millions of channels, beamed down to dishes on roofs. They carry internet. They carry phone calls. They carry data. Everything that needs to travel far and fast can go through space. Here's how it works. You have a device, a phone, a computer, a TV. It sends a signal up. Radio waves. Invisible waves of energy, traveling at light speed. The satellite, high above, catches these waves. Its antennas are like giant ears, listening. The satellite's computer processes the signal, figures out where it needs to go, then sends it back down, aimed precisely, to another antenna on Earth, to another device, to another person. Radio waves are amazing. They're invisible. You can't see them, you can't hear them, but they're everywhere. They carry information. They travel at the speed of light. They can go through space. They can go through air. They're perfect for communication. One satellite can see about 40% of Earth at once. That's a huge area. Millions of square miles. One satellite can handle millions of phone calls. Millions of internet connections. Millions of TV channels, all at the same time. It's like having a superpowered relay station floating in space. Think about that. One machine, floating in space, can handle millions of connections simultaneously. It can talk to millions of people at once. It can send millions of signals, all at the same time. It's incredible, it's powerful, it's what satellites do. The capacity is staggering. Modern communications satellites can process terabits of data per second. That's billions of bits every second. They're like supercomputers in space, constantly processing, constantly routing, constantly connecting. But here's the thing. The satellite is moving, or Earth is rotating, or both. So the connection doesn't last forever. A satellite in low orbit might only be visible for a few minutes. Then it's gone, over the horizon. But that's okay. There are other satellites, constellations of them, working together. When one disappears, another appears. The connection never breaks. It just switches satellites. This handoff happens automatically. Your device doesn't know it's happening. You don't notice. The connection just works. Seamlessly, constantly. It's like having an invisible network in the sky, always there, always working. The technology behind this is complex. Satellites communicate with each other, they coordinate, they know where they all are, they know when to hand off. They work as a team. A team in space. A team that keeps you connected. The coordination happens automatically. Satellites use inter-satellite links. They talk to each other. They share information. They know their positions. They know their neighbors. They know when to hand off connections. It's like a dance. A coordinated dance in space. A dance that keeps everyone connected. Even in the most remote places, this network works. On a ship in the middle of the ocean. On a plane flying across continents. In a village far from cities. The satellites are there. The connection is there. The internet is there. It's everywhere now, thanks to satellites. Imagine a researcher in the Arctic, far from civilization. But they can still access the internet. They can still communicate. They can still share their work. They can still be part of the global community. Satellites make this possible. They make remote work actually remote. They make anywhere accessible. Or think about a ship crossing the ocean. For weeks it's out of sight of land. But it can still have internet. It can still communicate. It can still stay connected. The crew can call home. They can access information. They can work. Satellites make the ocean connected. They make isolation a thing of the past. This is called handoff. Like when your phone switches from one cell tower to another. But in space, the satellite network is smart. It knows which satellites are where. It knows when to switch. It keeps you connected, even as satellites move. Some satellites stay in one place. Geostationary satellites. They orbit at exactly the right height and speed to match Earth's rotation. From the ground, they look like they're not moving. They're always in the same spot in the sky. Your satellite dish points at one place and never needs to move. The satellite is always there, always ready. These are perfect for TV, for radio, for things that need constant connection. But they're far away, 22,000 miles up. That's far. Signals take time to travel that distance. About a quarter of a second each way. That's noticeable. If you're on a video call through a geostationary satellite, there's a delay. You talk and half a second later the other person hears you. It's not instant. But for most things it doesn't matter. TV doesn't need to be instant. Radio doesn't need to be instant. Internet can work with a small delay. And the benefit is huge. One satellite can cover an entire continent. One satellite can serve millions of people. It's efficient. It's powerful. Satellite internet is getting faster. New satellites are being launched. Constellations of small satellites, working together. They're closer to Earth so signals travel faster. They're in low orbit so they move quickly. But there are many of them. When one moves out of view, another moves into view. The connection switches seamlessly. You don't notice. Your internet just works. These new constellations are changing everything. Companies are launching hundreds of satellites at a time. Thousands of them. They're creating networks in space. Networks that cover the whole planet. Networks that provide internet to everyone, everywhere. Some places on Earth are hard to reach. Remote villages, islands, ships at sea, planes in the air. These places can't have cables, they can't have cell towers. But they can have satellite dishes. They can point at the sky and connect. They can have internet, they can have phone service, they can be part of the connected world. This is changing everything. A school in a remote village can now access the same information as a school in a big city. A doctor on a ship can consult with specialists on land. A researcher in the Arctic can share data with colleagues around the world. Satellites are making the world smaller. They're making it more connected. Satellites also help during emergencies. When natural disasters destroy communication infrastructure, satellites can still work. They're above the damage. They can provide communication when everything else is down. They can help coordinate rescue efforts. They can help people contact loved ones. They're lifelines in the sky. When a hurricane hits, cell towers go down, power lines break, communication fails, but satellites keep working. They're above the storm, they're unaffected. They can provide emergency communication. They can help coordinate rescue. They can help people call for help. They can save lives. After major earthquakes, the same thing happens. Infrastructure is destroyed. Communication is cut. But satellites are there. They can provide emergency communication. They can help coordinate rescue efforts. They can help people find each other. They can help families reconnect. Some satellites are specifically designed for emergency use. They can be activated quickly. They can provide communication when it's needed most. They're emergency responders in space, always ready, always available, always there when disaster strikes. Emergency services use satellites regularly. Firefighters use them to coordinate. Search and rescue teams use them to communicate. Medical teams use them to get help. Satellites are part of emergency infrastructure. They're essential. They save lives. But satellites don't just connect people. They also watch our planet. They see things we can't see from the ground. They see the big picture. They see patterns. They see changes. They're our eyes in the sky, watching over Earth. Chapter 4. Watching Earth from above. Imagine you're trying to predict the weather. You need to see the whole picture. You need to see clouds forming over the ocean. You need to see storms moving across continents. You need to see patterns that stretch for thousands of miles. You can't do this from the ground. You need to be high up. You need to see Earth from above. This is what weather satellites do. They watch. They take pictures. They measure temperatures. They track clouds. They see storms forming before anyone on the ground knows they're coming. They're our early warning system. They're our weather eyes. Before satellites, weather prediction was limited. Meteorologists could only see what was nearby. They could see clouds overhead. They could see storms approaching. But they couldn't see the big picture. They couldn't see storms forming over the ocean. They couldn't see weather patterns developing far away. Satellites changed that. They gave us the big picture. They showed us what was coming. The first weather satellite launched in 1960. It was called TIROS. Television Infrared Observation Satellite. It took pictures of clouds from space. For the first time, we could see weather systems from above. We could see how big they were. We could see how they moved. We could see patterns we'd never seen before. Meteorologists were amazed. They could see entire weather systems. They could see how storms formed. They could see how they moved. They could see patterns that were invisible from the ground. It was like having a new sense. A sense that could see the whole planet at once. TIROS was a success. It took over 22,000 pictures in its first 78 days. It showed us hurricanes. It showed us storms. It showed us weather patterns we'd never seen. It proved that satellites could help us understand weather. It proved that space was useful. Before TIROS, weather forecasting was limited. Meteorologists could only see what was nearby. They could make predictions, but they were guesses. After TIROS, they could see the whole picture. They could see what was coming. They could make better predictions. They could save lives. Today, weather satellites are much more advanced. They don't just take pictures. They measure temperatures. They measure humidity. They measure wind speeds. They see in infrared, so they can see heat. They can see through clouds. They can see the structure of storms. They can predict where hurricanes will go. They can warn us days in advance. Modern weather satellites are like flying weather stations. They have instruments that measure everything: temperature, pressure, humidity, wind. They see invisible light. They see in infrared. They see in other wavelengths too. They're constantly watching, constantly measuring, constantly sending data back to Earth. The instruments on weather satellites are sophisticated. They can measure temperature differences of less than 1 degree. They can detect wind speeds from space. They can see through clouds. They can measure water vapor in the atmosphere. They can do things that were impossible before satellites. Weather forecasters use this data constantly. They feed it into computer models. The models predict what will happen. They show where storms will go. They show how weather will change. This prediction saves lives. It helps people prepare. It helps communities get ready. A hurricane is huge. It can be hundreds of miles across. From the ground, you can't see the whole thing. You're in it, or near it, but you can't see its shape. From space, you can see it all. The perfect spiral. The eye in the center. The bands of clouds wrapping around. You can see how it's moving. You can see how it's changing. You can predict where it will go. Weather satellites track hurricanes from birth to death. They see them form as small storms. They watch them grow. They see them strengthen. They predict their paths. They warn us when they're coming. They save lives by giving us time to prepare. Weather satellites save lives. They give us time to prepare. They give us time to evacuate. They give us time to get ready. Without them, hurricanes would hit with little warning. Storms would surprise us. Lives would be lost. But with satellites watching, we know. We see it coming. We're ready. But weather satellites aren't the only ones watching. There are satellites that map Earth. They take detailed pictures. They create maps more accurate than any map made from the ground. They can see roads, they can see buildings, they can see forests, they can see everything. Mapping from space is amazing. Satellites can take pictures of the entire planet. They can see every continent, every ocean, every island. They can create maps that are more accurate than any map made by walking around. They can see things that are too big to see from the ground. The resolution is incredible. Some satellites can see objects as small as a few inches across. They can read signs. They can see cars. They can see people. The detail is remarkable. The perspective is unique. The view from above reveals patterns invisible from the ground. Archaeologists use satellite images to find ancient sites. They can see patterns in the ground. They can see buried structures. They can discover things that were hidden for thousands of years. Satellites help us understand our past. They help us see what was there before. Google Maps uses satellite images. So does your phone's map app. Those detailed pictures of your neighborhood, taken from space, those street views, created from satellite data, those directions that tell you exactly where to turn, based on maps made from space. Mapping satellites are constantly updating. They take new pictures, they see what's changed. A new building goes up, a new road gets built, a forest gets cut down. Satellites see it. They update the maps. They keep our picture of Earth current. Some satellites watch for changes over time. They take pictures of the same place, year after year. They see forests shrinking. They see cities growing. They see ice caps melting. They see the planet changing. Slowly, gradually, but definitely. Scientists use these images to study climate change. They can measure how much ice has melted. They can count how many trees have been cut down. They can see how coastlines are changing. They can track changes that happen too slowly for us to notice from the ground. But from space, with pictures taken years apart, the changes are obvious. Climate change is slow. It happens over decades, over centuries. From the ground it's hard to see, but from space, with pictures taken years apart, the changes are clear. Ice caps are smaller, forests are fewer, coastlines are different. Satellites show us what's happening. They give us the data we need to understand. Some satellites can see very small things. Military satellites can see objects as small as a car. They can read license plates. They can see people. They're powerful. They're precise. But most satellites aren't that detailed. Most satellites see the big picture. They see patterns. They see changes. They see what matters. Satellites help with disasters. When there's a fire, satellites can see it. They can see how big it is. They can see which way the wind is blowing it. They can help firefighters know where to go. They can help people know when to evacuate. Wildfires are dangerous. They spread quickly. They're hard to predict. But satellites can see them from space. They can see where they started. They can see where they're going. They can help firefighters plan. They can help people evacuate. They can save lives. When there's a flood, satellites can see it. They can see how much area is underwater. They can see which roads are blocked. They can help rescue teams know where to go. They can help people find safe routes. Floods cover huge areas. From the ground, it's hard to see the full extent, but from space, satellites can see it all. They can see which areas are flooded. They can see which roads are passable. They can help rescue teams navigate. They can help people find safety. When there's an earthquake, satellites can see the damage. They can see which buildings collapsed. They can see which roads are blocked. They can help rescue teams prioritize. They can help save lives. Earthquakes cause damage over large areas. Satellites can see that damage from space. They can identify the worst hit areas. They can help rescue teams know where to go first. They can help save lives by showing where help is needed most. Satellites help farmers too. They can see which fields need water. They can see which crops are healthy. They can see which areas have pests. Farmers use this information to know when to water, when to fertilize, when to harvest. They can grow more food with less waste. Precision agriculture uses satellites. Farmers can see their fields from space. They can see which areas need attention. They can use water more efficiently. They can use fertilizer more efficiently. They can grow more food with fewer resources. It's better for the environment. It's better for the farmer. It's better for everyone. Satellites can detect plant health from space. Healthy plants reflect light differently than sick plants. Satellites can see this difference. They can identify which parts of a field need attention. They can help farmers treat only what needs treatment. They can reduce waste. They can increase yields. Some farmers use satellite data to create detailed maps of their fields. They show soil moisture. They show plant growth. They show which areas are productive. They help farmers make decisions. They help farmers optimize their operations. They turn farming into a science. Studies have shown that precision agriculture can increase yields by 20% or more. It can reduce water use by 30%. It can reduce fertilizer use by 40%. The numbers are impressive. The impact is real. Satellites are helping farmers feed the world more efficiently. Satellites can even count trees. Scientists use them to measure forests, to see how much forest we have, to see how much we're losing. They can count individual trees from space. Can you imagine looking down from hundreds of miles up and seeing individual trees? It's amazing. Forest monitoring from space is important. We need to know how much forest we have. We need to know how much we're losing. Satellites can help. They can count trees. They can measure forests. They can track changes. They give us the data we need to protect our forests. Researchers have used satellites to discover deforestation that was happening secretly. They've found illegal logging. They've tracked forest loss. They've provided evidence that's helped protect forests. Satellites are watchdogs. They're always watching. They never sleep. Satellites also monitor oceans. They can see oil spills. They can track pollution. They can monitor fish populations. They can study ocean currents. They can help protect marine life. The oceans are huge, but satellites can see them all. They can watch over them. They can help us understand them. Some satellites specialize in ocean monitoring. They measure sea surface temperatures. They track currents. They monitor algae blooms. They study marine ecosystems. They help us understand the oceans. They help us protect them. Ocean temperatures affect weather. They affect climate. They affect marine life. Satellites measure these temperatures constantly. They track changes. They help us understand how oceans affect climate. They provide data that's essential for climate science. Ocean currents are like rivers in the sea. They carry heat. They carry nutrients. They affect weather patterns. Satellites can track these currents. They can see how they move. They can help us understand ocean circulation. They can help us understand climate. Algae blooms can be harmful. They can kill fish. They can make water toxic. Satellites can detect these blooms early. They can see them forming. They can help us respond. They can help us protect marine life. They can help us protect people. Marine ecosystems are complex. They're hard to study from boats. But satellites can see the big picture. They can monitor entire ecosystems. They can track changes. They can help us understand marine life. They can help us protect it. But satellites don't just watch Earth. They also help us find our way. They help us navigate. They help us know exactly where we are. They're our guides in the sky. Chapter 5: Finding Your Way and Exploring Space. You're lost. You don't know where you are. You pull out your phone. You open a map app. In seconds, it shows you exactly where you are. A little dot on a map. Your location. Precise to within a few feet. How does it know? How does your phone know exactly where you are on this huge planet? The answer is GPS, Global Positioning System. It's a constellation of satellites. About 30 of them, circling Earth, constantly broadcasting signals. Each signal says two things: where the satellite is, and what time it is. GPS is everywhere now. It's in your phone. It's in your car. It's in ships. It's in planes. It's in farming equipment. It's in delivery trucks. It's become part of our daily lives. We use it without thinking. We trust it completely. But how does it work? Your phone receives these signals. It gets signals from multiple satellites at once. Usually 4 or more. For each signal it measures how long it took to arrive. It does this by comparing the time in the signal to the time on your phone. Here's the math. If you know when a signal was sent, and when you received it, you know how long it traveled. If you know how long it traveled, and you know the speed of light, you know the distance. If you know the distance to multiple satellites, and you know where those satellites are, you can calculate your position. It's geometry. It's beautiful. The math is called trilateration. It's like triangulation, but with distances instead of angles. You need at least 3 satellites to find your position on Earth. 4 satellites give you your position and elevation. More satellites make it more accurate. Your phone uses as many as it can see. The more satellites you can see, the better. In open areas you might see 10 or more. In cities with tall buildings you might see fewer. But your phone tries to use as many as possible. It calculates your position from all of them. It averages the results. It gives you the most accurate position possible. The accuracy depends on many factors: signal strength, number of satellites, atmospheric conditions. But even in poor conditions, GPS is usually accurate to within a few meters. That's good enough for most uses. For navigation, for finding your way. But the math requires precision. If the time is off by 1 second, your position would be off by 186,000 miles. That's how far light travels in 1 second. So GPS satellites have the most accurate clocks ever built. Atomic clocks. They're accurate to within a few nanoseconds. A nanosecond is 1/1000th of a second. That's how precise they need to be. Atomic clocks are amazing. They use atoms to keep time. Specifically, they use cesium atoms. These atoms vibrate at a very specific frequency. The clocks count these vibrations. They're incredibly precise. They don't drift. They don't slow down. They're the most accurate timekeepers we've ever built. GPS was originally built for the military. The US military wanted to know exactly where their ships and planes and soldiers were. But in the 1980s, they opened it up. They made it available to everyone. For free. Now billions of devices use it. Your phone, your car, ships, planes. Even farming equipment uses GPS to plant crops in perfect rows. The military still uses GPS, but so does everyone else. The system was designed for military use, but it's become essential for civilian life too. It's used for navigation, for timing, for synchronization. It's everywhere. The decision to make GPS free was important. It changed everything. It made navigation available to everyone. It made it possible for anyone to know where they are. It democratized location. It made the world more navigable. Before GPS, navigation was hard. You needed maps, you needed to know where you were, you needed landmarks. GPS changed all that. Now, anyone can know exactly where they are, instantly, accurately, for free. GPS has saved countless lives. If you're lost in the wilderness, GPS can guide rescuers to you. If you're in a car accident, your phone can send your exact location to emergency services. If you're hiking and get turned around, GPS can show you the way back. It's become essential. We depend on it. We trust it. But GPS isn't the only navigation system. Russia has GLONASS, Europe has Galileo, China has Beidou. They all work the same way. Satellites broadcasting signals, devices receiving them, calculating position. They're all constellations of satellites, working together, helping us find our way. Having multiple systems is good. It provides backup. If one system fails, others can take over. It also provides better coverage. In cities with tall buildings, you might not see all GPS satellites. But you might see GLONASS satellites. Or Galileo satellites. Your phone uses all of them. It picks the best signals. It gives you the most accurate position. But satellites don't just help us navigate Earth. They also help us explore space. They're our eyes and ears beyond our planet. They study the sun. They study other planets. They study stars and galaxies. They see things we can't see from Earth. The Hubble Space Telescope is a satellite. It orbits Earth, but it looks outward. It looks at stars, at galaxies, at nebulas, at the universe. It's taken over 1 million pictures. It's shown us things we never imagined. Galaxies colliding, stars being born, planets around other suns. It's changed how we understand the universe. Hubble was launched in 1990, but it had a problem. Its mirror was flawed, it couldn't focus properly, the pictures were blurry. But astronauts fixed it, they installed corrective optics, they made it work. And it's been working ever since, taking amazing pictures, showing us the universe. The flaw was tiny, less than a hair's width, but it was enough to ruin the images. Scientists were devastated. But they didn't give up. They designed a fix. Astronauts installed it. And Hubble became the telescope it was meant to be. Hubble has been up there for over 30 years. It's been repaired by astronauts, it's been upgraded, it's still working, still taking pictures, still showing us the cosmos. It's one of the most successful satellites ever built. Astronomers have used Hubble to study everything: stars, galaxies, nebulas, planets. They've made discoveries that changed our understanding of the universe. They've seen things we never imagined. Hubble has been one of the most important scientific instruments ever built. Hubble helped determine the age of the universe. It measured how fast the universe is expanding. It found evidence of dark energy. It discovered planets around other stars. It studied black holes. It did science that was impossible from the ground. Every discovery from Hubble has been important. Every picture has told a story. Every observation has added to our knowledge. Hubble has been a window on the universe. A window that shows us things we could never see otherwise. A window that has changed how we understand everything. The science from Hubble has been published in thousands of papers. It's been cited by researchers around the world. It's been used in textbooks. It's become part of our understanding of the universe. Hubble hasn't just taken pictures, it's changed science. The James Webb Space Telescope is newer, it's bigger, it's more powerful, it can see farther, it can see things Hubble can't see. It's studying the earliest galaxies. The first stars. The birth of the universe. It's answering questions we've been asking for centuries. Webb is different from Hubble, it sees in infrared. It can see through dust. It can see things that are too faint for Hubble. It can see farther back in time. It's showing us the early universe, the first galaxies, the first stars. It's rewriting our understanding of cosmic history. Infrared light is different from visible light. It has longer wavelengths. It can pass through dust clouds. It can reveal things hidden in visible light. Webb uses this to see deeper into space, to see farther back in time, to see the universe's earliest moments. The first images from Webb were stunning. They showed galaxies we'd never seen. They showed details we'd never imagined. They showed the universe in a new light. Literally, Webb is opening new windows on the cosmos. It's showing us things we never knew existed. One of the first images showed a star being born. It showed clouds of gas and dust. It showed the early stages of star formation. It showed us something we'd only imagined before. Now we could see it, really see it, in detail, in color. It was beautiful. Another image showed thousands of galaxies, each one a collection of billions of stars, each one a universe in itself. The image was taken in a tiny patch of sky, a patch that looked empty. But it wasn't empty. It was full of galaxies, full of stars, full of worlds. The universe is vast. Webb is showing us just how vast. Webb is also studying exoplanets, planets around other stars. It can analyze their atmospheres, it can detect water, it can detect gases. It can look for signs of life. It's opening new possibilities. It's asking new questions. It's searching for answers. But not all space satellites look outward. Some look at the sun. They study solar flares. They study the solar wind. They watch for storms on the sun that could affect Earth. These storms can knock out power grids. They can disrupt satellites. They can cause problems. So we watch the sun, we study it, we try to predict when it will cause trouble. Solar storms are dangerous. They can send charged particles toward Earth. These particles can disrupt electronics. They can knock out power. They can damage satellites. So we watch the sun. We try to predict storms. We try to protect ourselves. The sun goes through cycles. Sometimes it's quiet. Sometimes it's active. During active periods, solar storms are more common. Satellites watch for these storms. They detect them early. They give us warning. They help us prepare. When a major solar storm is coming, power companies can prepare. They can adjust their grids. They can protect their equipment. They can prevent blackouts. Satellites give us this warning. They help us protect our infrastructure. They help us stay safe. Some satellites are positioned to watch the sun constantly. They're like early warning systems. They detect solar flares. They measure solar wind. They watch for coronal mass ejections. They're our eyes on the sun. They're our protection. Some satellites study other planets. They orbit Mars. They orbit Jupiter. They orbit Saturn. They take pictures. They measure things. They send data back to Earth. They're our robotic explorers. They go where we can't go yet. They see what we can't see yet. Mars has several satellites orbiting it. They take pictures of the surface. They study the atmosphere. They help the rovers navigate. They're like scouts. They go first. They see what's there. They help us plan future missions. The Mars Reconnaissance Orbiter has been there since 2006. It's taken thousands of pictures. It's studied the surface in detail. It's found evidence of water. It's helped us understand Mars. It's been essential for planning rover missions. Other Mars orbiters study the atmosphere. They measure temperatures. They track dust storms. They study the weather. They help us understand Mars's climate. They help us prepare for future human missions. They're building the knowledge we need to live on Mars. The Mars rovers use satellites to communicate with Earth. The rovers are on the ground, exploring. But they can't talk directly to Earth. The signals are too weak. So they talk to satellites orbiting Mars. The satellites relay the signals to Earth. They're like cell towers in space. They keep us connected to our robots on other worlds. Mars is far away, really far. Even at light speed, signals take time. When Mars is closest to Earth, it's still 34 million miles away. Signals take about 3 minutes to travel one way. When Mars is farthest, it's 250 million miles away. Signals take over 20 minutes. Communication is slow. But satellites make it possible. The rovers can't carry big antennas. They're small, they're mobile, they need to save power. So they use small antennas. They send weak signals. The satellites orbiting Mars have big antennas. They can receive those weak signals. They can amplify them. They can send them to Earth. They're the middlemen, the relay stations, the bridges between Mars and Earth. Without these satellites, the rovers would be silent. We wouldn't know what they found. We wouldn't see their pictures. We wouldn't get their data. The satellites make the rovers useful. They make exploration possible. They're essential. Satellites help us understand climate change too. They measure temperatures. They measure sea levels. They measure ice. They track changes over decades. They give us data, hard facts. They show us what's happening to our planet. They help us understand what we need to do. Climate satellites are essential. They give us the data we need to understand climate change. They show us what's happening. They help us make decisions. They're our eyes on the planet. They're helping us understand our impact. Some satellites specialize in measuring greenhouse gases. They can detect carbon dioxide. They can measure methane. They can track where these gases come from. They can see which countries are producing the most. They provide data that's hard to argue with. They show us the truth. Other satellites measure sea levels. They've been doing this for decades. They've shown that sea levels are rising. Slowly but steadily. They've provided the data that proves climate change is real. They've given us the evidence we need to act. Scientists use this satellite data in climate models. They feed it into computers. The computers predict what will happen. They show us possible futures. They help us understand what we need to do. They help us plan. They help us prepare. All of these satellites: navigation, communication, weather, mapping, science. They've changed everything. They've changed how we live, how we work, how we explore. They've made the world smaller. They've made space closer. They've connected us. They've guided us. They've shown us things we never could have seen. But what's next? What's coming? The sky above us is getting busier. New satellites are being launched every week. New technologies are being developed. New possibilities are opening up. The future of satellites is being written right now. Chapter 6: The Future Above Us. Right now there are about 5,000 active satellites orbiting Earth. But that number is growing fast. Really fast. Companies are launching hundreds at a time. Constellations of small satellites, working together, providing internet to the whole planet, covering every square inch with connectivity. The growth is exponential. Every year, more satellites are launched than the year before. Companies are investing billions. Governments are expanding their fleets. Students are launching their own. The sky is getting crowded, but it's also getting more useful. Starlink is one of these. It's a project to put tens of thousands of small satellites in orbit. They're in low orbit, so signals travel fast. They're close together, so coverage is complete. The goal is internet for everyone, everywhere. Even in the most remote places. Even in the middle of the ocean. Even in the deepest forest. Starlink has already launched thousands of satellites. They're providing internet to people who never had it before. Remote villages. Ships at sea. Planes in the air. They're connecting the unconnected. They're bringing the internet to places that cables can't reach. The impact is real. People in remote areas can now access the internet. They can learn. They can work. They can connect. They can be part of the global community. Satellites are making this possible. They're bridging the digital divide. They're connecting everyone. But Starlink isn't alone. Other companies are launching their own constellations. OneWeb, Amazon's Project Kuiper. They're all racing to provide global internet. They're all using satellites. They're all trying to connect the world. OneWeb has launched hundreds of satellites. They're building their own constellation. They're providing internet to remote areas. They're connecting people who were disconnected. They're making the internet global. Amazon's Project Kuiper plans to launch thousands of satellites. They're still in development. But they're serious. They want to provide global internet. They want to compete. They want to connect everyone. China is also building constellations. So is Europe. So are other countries. Everyone wants global internet. Everyone wants to connect the world. The race is on. The sky is getting crowded. But it's also getting more connected. This is changing things. Internet used to require cables. Or cell towers. Or something physical on the ground. But with enough satellites, you don't need that. You just need a small dish. Point it at the sky. Connect. You're online. It's that simple. But this creates challenges. The sky is getting crowded. There are concerns about space traffic. What happens if satellites collide? What happens if there are too many? What happens to the night sky? Will we still be able to see stars? Will satellites block our view? These are real questions. Scientists are studying them. Companies are working on solutions. Some satellites are designed to be less reflective. They won't shine as bright. They won't interfere with astronomy. Some are designed to automatically avoid collisions. They can move out of the way. They're smart. Astronomers are concerned about satellite constellations. They worry that bright satellites will interfere with observations. They worry that the night sky will be polluted. They worry that astronomy will become harder. These are valid concerns. They're being addressed. Companies are working on solutions. Some satellites are painted darker. They reflect less light. Some have sunshades. They block sunlight from hitting reflective surfaces. Some are designed to be less visible. They're trying to minimize their impact on astronomy. Automated collision avoidance is also important. Satellites can detect when they're on a collision course. They can fire small thrusters. They can move out of the way. They can avoid collisions automatically. They're getting smarter. They're getting safer. The technology is improving. Satellites are getting better at avoiding collisions. They're getting better at being invisible. They're getting better at coexisting with astronomy. The future is about balance. Balance between utility and preservation. Balance between progress and protection. Space traffic management is becoming important. We need to track all satellites. We need to predict collisions. We need to coordinate launches. We need to manage space like we manage air traffic. It's a new challenge, but we're working on it. Space agencies around the world are working together. They're sharing data. They're coordinating. They're trying to prevent collisions. They're trying to keep space safe. It's a global effort, a necessary effort. The problem is complex. There are thousands of objects up there. They're all moving. They're all in different orbits. Predicting collisions is hard. But it's getting better. We're getting better at tracking, better at predicting, better at managing. There's also the problem of space junk, old satellites, broken satellites, pieces of rockets, all of it still up there, orbiting, moving fast, dangerous. A tiny piece of space junk, moving at 17,000 miles per hour, can destroy a satellite. It's like a bullet, but bigger. Space junk is a growing problem. There are millions of pieces up there. Most are small. But even small pieces are dangerous at those speeds. They can damage satellites. They can threaten the space station. They're a hazard we need to deal with. The problem is getting worse. Every launch creates more debris. Every collision creates more fragments. The debris multiplies. It spreads. It becomes harder to track. It becomes harder to avoid. It's a problem that grows over time. Some pieces of space junk are large. Old satellites. Rocket stages. They're dangerous. They can cause major collisions. If they collide, they create thousands of fragments. Each fragment is dangerous. Each fragment can cause more collisions. It's a chain reaction, a cascade, a problem that feeds on itself. Scientists are studying this problem. They're developing solutions. They're testing cleanup methods. They're trying to prevent future debris. They're working to make space safer. They're working to protect our satellites. They're working to protect our future in space. Scientists are working on cleaning up space. Some satellites are designed to grab space junk and pull it down. Some are designed to push junk into the atmosphere, where it will burn up. Some are designed to repair other satellites, to refuel them, to extend their lives. Cleanup missions are being planned. Satellites that can capture debris. Satellites that can deorbit old satellites. Satellites that can make space safer. It's expensive, it's difficult, but it's necessary. Some cleanup satellites use nets. They catch debris like a fishing net. Others use harpoons. They spear debris and pull it down. Still others use robotic arms. They grab debris and deorbit it. Different methods for different situations. The first cleanup mission is already being tested. It's a proof of concept. If it works, more will follow. We need to clean up space. We need to make it safer. We need to protect our satellites. We need to protect our future in space. The cleanup satellite will test different methods. It will try using nets. It will try using harpoons. It will try using robotic arms. It will see what works best. It will learn. It will improve. It will pave the way for future cleanup missions. If successful, this could change everything. We could start cleaning up space. We could remove dangerous debris. We could make space safer. We could protect our satellites. We could protect our future. It's a small step, but it's an important one. It's a step toward a cleaner space. Some companies are already planning commercial cleanup services. They want to offer debris removal as a service. They want to make money cleaning up space. It's a new industry, a necessary industry, an industry that could help protect space for everyone. The future might see satellites that can repair themselves, satellites that can refuel, satellites that can upgrade themselves, satellites that last for decades instead of years. This would reduce waste. It would reduce the need for new launches. It would make space cleaner. Self-repairing satellites are being developed. They could fix themselves when damaged. They could replace broken parts. They could extend their own lives. This would be revolutionary. It would change how we think about satellites. Imagine a satellite that can detect damage. It notices a broken solar panel. It uses a robotic arm to replace it. It fixes itself. It continues working. This isn't science fiction. It's being developed. It's the future. Some satellites already have limited self-repair capabilities. They can adjust their orbits. They can reorient themselves. They can work around problems. But true self-repair is still in development. When it arrives, it will change everything. Satellites are also getting smaller. CubeSats are becoming more powerful. Students are building them. Amateur radio operators are building them. Companies are building them. Space is becoming accessible. You don't need to be a government. You don't need billions of dollars. You can put something in space. CubeSats are democratizing space. They're making it accessible. They're allowing more people to participate. They're opening space to everyone. This is important. Space shouldn't just be for governments and big companies. It should be for everyone. Some companies want to put satellites around the moon, to provide internet there, to support future moon bases, to help us explore. The moon is far, but it's reachable. And if we're going to live there, we'll need satellites, we'll need communication, we'll need navigation, we'll need all the things we have on Earth. Lunar satellites are being planned. They would provide communication for moon bases. They would help with navigation. They would support exploration. They would be essential for living on the moon. The moon is far from Earth. Direct communication is hard. But with satellites around the moon, we could stay connected. We could have constant communication. We could have navigation. We could have all the infrastructure we need. Some companies are already planning lunar satellite networks. They're designing satellites specifically for the moon. They're thinking about lunar communication. They're preparing for a future where people live on the moon. Satellites will be essential for that future. The moon presents unique challenges. It's far from Earth. Communication takes time. The lunar environment is harsh. But satellites can help. They can provide communication. They can provide navigation. They can support lunar bases. They can make living on the moon possible. NASA and other space agencies are planning lunar missions. They're planning to build bases. They're planning to establish a presence. Satellites will be part of that. They'll be the infrastructure. They'll be the communication network. They'll be essential. Some companies are even planning to mine the moon. They want to extract resources, water, helium-3, materials that could be valuable. Satellites would help with this. They would guide mining operations. They would provide communication. They would support the infrastructure needed for lunar mining. Lunar mining could provide resources for space exploration. Water could be turned into rocket fuel. Helium-3 could be used for fusion power. Rare earth elements could be valuable. The moon could become a resource base. Satellites would make this possible. The moon has resources that Earth doesn't have enough of, or resources that are hard to get. Mining the moon could solve these problems. It could provide materials for space exploration. It could support colonies. It could enable deeper space missions. Satellites would be essential for all of this. But mining the moon is still in the future. The technology needs to be developed. The economics need to make sense. The logistics need to be worked out. But satellites would be part of it. They would be the infrastructure. They would make it possible. Future satellites might be built in space. Instead of launching them from Earth, we might build them in orbit, using materials from asteroids, using 3D printers, building them where they'll live. This would be cheaper, it would be easier, it would open up new possibilities. In-space manufacturing is being developed. We could build satellites in orbit. We could use materials from space. We could avoid the cost of launching. This would be a game changer. It would make space more accessible. The idea is simple. Instead of building satellites on Earth and launching them, we could build them in space. We could use 3D printers. We could use materials from asteroids. We could assemble them in orbit. This would eliminate the need for rockets large enough to carry complete satellites. It would change the economics of space. Some companies are already testing this. They're developing space-based 3D printers. They're testing materials. They're planning space factories. It sounds like science fiction, but it's becoming real. The technology is advancing. The possibilities are expanding. Some satellites might help with asteroid mining. They might scout for valuable asteroids. They might guide mining operations. They might help us extract resources from space. This sounds like science fiction, but it's being planned. Companies are working on it. Asteroid mining could provide resources for space exploration. Water, metals, materials we need. Satellites would be essential for this. They would scout. They would guide. They would support mining operations. The idea is to find asteroids rich in valuable materials, platinum, gold, rare earth elements. Water that could be used for fuel. Satellites would help locate these asteroids. They would study them. They would help plan mining operations. They would be the eyes and ears of asteroid mining. This is still in the planning stage, but companies are serious about it. They're developing the technology. They're planning missions. They're thinking about how satellites would help. It's a future possibility, one that satellites would make possible. Some asteroids are worth trillions of dollars in materials, but getting to them is hard. Mining them is harder. Satellites would make it easier. They would provide the information needed. They would guide the operations. They would be essential partners in space mining. Satellites might help us live on Mars. Communication satellites around Mars. Navigation satellites. Weather satellites. All the infrastructure we need to survive on another planet. Satellites would be essential. They'd be our lifeline to Earth. They'd be our guide on a new world. Mars satellites are already being planned. They would provide communication. They would help with navigation. They would support future Mars missions. They would be essential for living on Mars. But with all this growth comes responsibility. We need to be careful. We need to think about the long term. We need to protect space. We need to keep it clean. We need to make sure future generations can still explore, can still discover, can still look up at a starry sky. Space is a shared resource. We need to protect it. We need to use it responsibly. We need to think about the future. We need to make sure space remains accessible. We need to make sure it remains beautiful. The future of satellites is exciting. It's full of possibilities, but it's also full of challenges. How do we manage space traffic? How do we clean up space junk? How do we make sure everyone has access? How do we protect the night sky? These are questions we're asking now, questions we need to answer. These are important questions. They need answers. They need solutions. They need cooperation. Space is too important to leave to chance. We need to work together. We need to plan. We need to protect. International organizations are forming to address these issues. They're creating rules, they're establishing guidelines, they're trying to manage space responsibly. It's a global effort, it requires cooperation, it requires everyone to work together. Some countries are already taking action. They're requiring satellite operators to plan for end of life. They're requiring collision avoidance systems. They're trying to make space safer. They're trying to protect it for future generations. But one thing is certain, satellites aren't going away. They're becoming more important, more essential, more part of our daily lives. The quiet machines above us are getting busier. But they're also getting more useful. They're connecting us. They're guiding us. They're showing us things we never could have seen. The trend is clear. More satellites, more capabilities, more integration into daily life. We're building a world that depends on satellites, a world where they're essential, a world where they're part of everything we do. Think about your daily life. You wake up and check the weather. That data comes from satellites. You use GPS to navigate. That's satellites. You watch TV or use the internet. That might be satellites too. You're using satellites constantly, probably without even knowing it. Satellites have become invisible infrastructure, like roads or power lines. We don't think about them, we just use them. They're there, they work, they make our lives easier, they make things possible that weren't possible before. But this infrastructure is in space, it's orbiting, it's falling constantly, it's balancing physics and engineering. It's amazing, really, that we've built this. That we've made it work, that we've made it reliable, that we've made it essential. The sky above us is changing, it's getting more crowded. But it's also getting more connected, more useful, more amazing. The future is being written in orbit, right now, by thousands of quiet machines, doing their work, circling our planet, helping us understand our world and reach beyond it. And now the thoughts begin to settle, like satellites finding their orbits. We've drifted through the silent world above, from the first beeping Sputnik to the thousands of satellites circling us today. You've learned how they stay up by constantly falling, how they connect continents with signals traveling at light speed, how they watch our weather and map our planet, how they guide us home and help us explore space. It's been a long journey. We've traveled from the first artificial satellite to the thousands that circle us now. We've learned about orbits and gravity, about communication and navigation, about watching Earth and exploring space. We've seen how satellites have changed everything, how they've transformed our world. You are part of this story. Every time you use GPS, you're talking to satellites. Every time you watch TV, you might be receiving signals from space. Every time you check the weather, you're seeing data from satellites watching above. These quiet machines are part of your daily life, even though you probably never think about them. Think about that. Right now, as you're listening, satellites are working for you. They're helping you navigate, they're bringing you information, they're connecting you to the world. They're doing all of this, silently, constantly, without you even knowing. Right now, as you rest, satellites are working, they're connecting phone calls across oceans. They're watching storms form, they're taking pictures of Earth. They're guiding ships and planes, they're studying the universe. They're doing all of this, silently, constantly, above us. The work never stops. Satellites work 24 hours a day. They work in sunlight and shadow. They work in heat and cold. They work constantly. They never take breaks. They never get tired. They just keep going, around and around, doing their jobs. We've come a long way since that first beeping ball in 1957, from one satellite to thousands, from simple beeps to complex networks, from curiosity to necessity, Satellites have transformed our world. They've made it smaller. They've made it more connected. They've made it more understandable. In just over 60 years, we've gone from one satellite to thousands. We've gone from simple beeps to complex networks. We've gone from curiosity to necessity. Satellites have become essential. They've become part of our infrastructure. They've become part of our lives. The future holds even more. More satellites. More capabilities. More possibilities. The sky above us is getting busier, but it's also getting more useful. These quiet machines will keep working. They'll keep connecting us. They'll keep guiding us. They'll keep showing us things we never could have seen. The future is exciting. New satellites are being launched every week. New technologies are being developed. New possibilities are opening up. The sky above us is changing. It's getting more crowded. But it's also getting more useful, more amazing, more connected. So rest easy, knowing that above you, right now, thousands of satellites are circling. They're working, they're helping. They're part of the quiet infrastructure that makes modern life possible. They're our attendants in space, our eyes in the sky, our guides in the dark. These quiet machines are always there, always working, always helping. They're part of the background of modern life. We don't think about them, we don't see them. But they're there, they're essential, they're part of everything we do. If you happen to still be awake, you can go ahead and watch the next video. But for now, let the thoughts of satellites and orbits drift away like signals fading into space. You are here, in this moment, resting. The satellites will keep working. Everything will be there when you wake. For now, just rest, just breathe, just be. The satellites will keep circling, they'll keep working, they'll keep helping. They'll be there when you wake. They'll be there tomorrow. They'll be there always. Quiet, constant, reliable, like the stars but closer, like the moon, but made by us. From that first beeping Sputnik to the thousands circling now, we've come a long way. We've learned to build machines that fall forever. We've learned to use space for our purposes. We've learned to connect the world. We've learned to watch our planet. We've learned to explore the universe. In just over 60 years, we've transformed space from a frontier into a workplace. We've filled it with machines. We've made it useful. We've made it essential. We've built infrastructure in the sky. We've created a network that spans the globe. We've changed everything. Satellites are more than machines. They're extensions of ourselves. They're our eyes in the sky. They're our voices across oceans. They're our guides in the dark. They're our connection to the world. They're our link to space. Each satellite is a testament to human ingenuity. Each one represents thousands of hours of work. Each one is a marvel of engineering. Each one is doing something useful. Each one is part of a larger system, a system that connects us all, a system that makes modern life possible. The future is bright. More satellites are coming, more capabilities, more possibilities. The sky above us is getting busier, but it's also getting more useful. These quiet machines will keep working. They'll keep evolving. They'll keep helping us understand our world and reach beyond it. So as you drift towards sleep, remember this. Above you, right now, thousands of satellites are circling. They're working. They're helping. They're part of the quiet infrastructure that makes modern life possible. They're our attendants in space, our eyes in the sky, our guides in the dark. They're always there, always working, always helping. Sweet dreams, and may your sleep be as peaceful as a satellite's steady orbit.